Hello everyone, welcome to our presentation. My name is Serdar Sarıgül and on behalf of our research team, I will be presenting today our paper, Pedestrian Detection and Target Classification in Urban Forest and Environment using FMCW Automotive Radar and CNN. Recent advancements in AI in artificial intelligence have accelerated the development of autonomous vehicles capable of real-time decision making in complex environments. However, adverse weather conditions like having fog, rain, snow, and or windy conditions may pose serious challenges to those sensor reliability, especially for pedestrian detection. Standards like ISO 5469 and ISO 8800, focusing on functional safety and artificial intelligence, emphasize the need for reliability, explainability, and redundancy in AI systems. In our study, we use FMCW radar, which is known for its resilience and cost efficiency. And we apply CNN on microdoppler features to outperform traditional classifiers like support vector machine. We also focus on windy urban forest scenarios, which leads us to the central aim of our paper, to simulate and evaluate CNN-based pedestrian detection in windy urban environments using realistic 3D tree modeling to address the following two key questions. How does wind-induced motion affect detection? Can CNN maintain high accuracy under such conditions? In the upcoming slides, I will be walking you through our simulation setup, CNN architecture, simulation results, and finally the conclusion. Now let's look at the scenario design. In our scenario, we simulate an eco vehicle navigating a typical urban road, and it is equipped with an FMCW radar working at 77 GHz. Alongside, there is a car parked on the side of the road, a pedestrian randomly walking toward the road, and a tree with branches swaying in the wind to represent the vegetation. The purpose here is to evaluate if a CNN can detect and classify the pedestrian correctly, even when the radar signals are cluttered by dynamic elements like moving the tree branches. We define 6 sub-scenarios, as you can see on the right-hand side, with different combinations of the pedestrian, the parked car, and the tree to analyze detection accuracy in isolation and in cluttered environments. We started by specifying the individual radar targets as a stationary parked car, a pedestrian with varying height and speed, and a tree. While the car and pedestrian models were readily available in MATLAB, the tree had to be modeled from scratch. That's why we use a detailed 3D model structured with around 99,000 triangular surface patches to simulate a realistic tree. For calculating the radar cross-section of the tree, we used the physical optics method suitable for high-frequency approximations like 77 GHz. We also added micro-RCS fluctuations based on the swirling 4 model. This model accounts for both large scatterers such as tree trunk and many other small ones like leaves, and the RCS values varying between radar pulses. Actually, this feature is making it more realistic for our simulation. While building the tree model, we considered the trunk, the branches, and also the leaves. Importantly, we added the effect of wind to mimic the real-world signal noise. To validate our model, we calculated the mean RCS from 3 aspect angles and confirmed that the simulated swirling 4 distribution aligned with the theoretical predictions, as you can see right hand side. There is a reference paper from Özlem Kılıç, and her research showed that tree motion under wind can heavily interfere with pedestrian detection, and our results support the same concept. As seen in the spectrograms on the right hand side, the human signature is clearly visible in isolation, but becomes indistinguishable when combined with the other targets, which proves the challenge of the detection in forestry environments. To detect pedestrians accurately in our scenario, we integrated a 77 GHz long-range radar with a 100-meter detection range. And this is consistent with industry use in some adaptive cruise control radar systems. Following the literature research, we selected linear frequency modulation over frequency shift keying due to its superior range resolution. Our radar uses a 150 MHz bandwidth, resulting in a 1 meter range resolution, which is ideal for distinguishing between closest space targets like pedestrians and static objects. The radar can track targets moving up to 30 km per hour, which includes typical pedestrian speeds. The figures illustrate both the waveform and the spectrogram, showing how our signal is structured in time and frequency domains on the right hand side. To simulate real-world complexity, we randomize some key elements in our environment, such as pedestrian characteristics, object positioning, and vehicle speeds, while maintaining the structural consistency. Each radar return was transformed into a spectrogram using the short-time Fourier transform for microdoppler feature extraction. We generated 21,000 labeled data across 6 distinct sub-scenario categories, which each class equally represented to ensure balanced training. The data set was then split 80% for training, 20% for validation across all categories. The CNN was specifically designed for the classification in noisy environments, especially where pedestrian microdoppler signatures might be masked by moving trees. The architecture processes high-res RGB spectrograms, starting with a 2D convolutional layer for basic feature extraction, followed by multiple layers of convolutional and pooling for feature learning. A fully connected layer outputs class probabilities via a softmax layer, enabling multi-class target classification. Finally, we tuned this model using the ADAM optimizer, a batch of 64 and ReLU activations. This setup offered a solid trade-off between computational load and classification accuracy. The CNN achieved an overall classification accuracy of 87.12%, as can be seen in the graph. This strong performance confirms the effectiveness of our scenario design and the spectrogram generation, especially under noise-heavy conditions. As evident from the confusion matrix figure on the left, sub-scenarios involving pedestrians, parked car, or boat achieved detection and classification accuracy exceeding 90%. These classes generated distinctive Doppler signatures that the CNN could identify reliably. Despite strong overall performance, the CNN struggled with 2 specific categories, which is tree only and pedestrian plus tree, where classification accuracy dropped to 67% range. This is largely due to the microdoppler interference caused by tree branches, which mimics pedestrian motion or dominates the human signature. As a result, the CNN often confuses the two, especially when the pedestrian's microdoppler signature is subtle or masked. In conclusion, this study demonstrated that the classification accuracy of radar-based pedestrian detection systems might be significantly affected in environments with dense vegetation in some cases. In particular, it reveals that the CNN might struggle to distinguish human microdoppler signatures from similar patterns caused by the branches. So, as to address that, we propose 4 main improvement directions for the future. First, applying singular value decomposition to filter vegetation noise before spectrum generation for cleaner inputs. Secondly, incorporating complementary sensors such as LiDAR or cameras with sensor fusion, but this is a costly solution and requires some big modifications. Third, enhancing the model structure with attention mechanisms, or finally, using domain-specific data augmentation technique might be applicable. Together, These improvements could push the system's accuracy above 95% as expected. By enhancing both safety and performance in autonomous driving applications, especially under adverse environmental conditions, while keeping the solution cost effective and scalable. Thank you for your time today, for your participations, and I will be ready to take your questions now.